In the last couple of sections, we saw that changing from rectangular to a different coordinate system was pretty helpful for more complicated shapes or shapes that had certain properties, round or spherical. But what if we want to come up with a brand new coordinate system, basically? We want to change to another coordinate system that might be helpful. How do we figure out what that little piece of volume actually turns into, or that little piece of area, what does it turn into? So far we've been doing this geometrically. We kind of drew the picture and figured out what that had to be. But is there a way to do it mathematically? Well, if you kind of think of how we would do this in one variable, we have an integration method called U substitution. Generally, if we were going to do a U substitution, we take a part of this function f here and we say, let u be some function of x that was buried inside of there. Well, according to this, if u is some function of x, that means we should be able to solve for x, and so x is some other function of u. So now we can kind of get an idea of how to transform this into our new variable. What we could do is we could replace all the x's with that new function, so this f of h of u. So we replaced all the x's with that. Now we'd also need to replace the dx. Well, dx would be h prime of u du. So h prime of u du. Now notice we just didn't replace this letter with a derivative of that letter. Dx wasn't replaced with just du. We have this factor in here. This is the scaling factor as we're going from one set of units to another set of units. And you see this anytime we convert units. Like if we're going from metric to the imperial system or American system, right? If we go from inches to centimeters, right? It's just not inches equals centimeters. There's 2.54 centimeters in an inch, right? There's that conversion factor that goes in there. Well, this is kind of the way it worked in Calc 1, and that was kind of the conversion factor that came along. But what happens now that we have functions of several variables, like if we had this, like if I had some function of x and y, let's say over some area. So let's say we're finding some volume here. Well, generally, since we have two variables, a lot of times we're going to replace them with two brand new variables. So let's say h is some g of u and v, and y is some other function of u and v. Well, if we go to replace this, it would be pretty obvious that we'd replace all the x's with whatever this function was, because that's what we said it was equal to. We'd replace all the y's with this new function of u's and v's. But then we'd have to replace dA with something. Now, you might assume, and now here, remember, this would be, hold on. I'm back. This dA here, remember, is like dy dx or dx dy. I'll just go dx dy. You might assume that over here, then this would just convert to du dv or dv du. But it doesn't. It's got this scaling factor. Notice here the scaling factor is based off of the derivative. Well, it's actually going to be based off the derivative here as well. So we're going to define a new operator real quick, and it's called the Jacobian. Here's what it says. It says the partial of x and y with respect to u and v is going to be the partial of x with respect to u, partial of x with respect to v, the partial of y with respect to u, partial of y with respect to v, and then we're going to do the determinant of that matrices. So multiply down the main diagonal, u partial y with respect to v, minus the other diagonal, partial x with respect to v, partial y with respect to u. All right, so this is a new operator called the Jacobian. The way you kind of see how it works, you start with the first variable up here, and then you take the derivative with respect to the variables on the bottom that goes across the first row. Then you move over to the next variable, you take its derivative with respect to all the variables in the second row. And if we have a 3s, then we do third row, so on and so forth. Now, that actually ends up being our conversion factor when we go over here. Now, since we're converting area units, we're going to want this to be positive. So this is going to be the Jacobian of x and y with respect to u and v, du dv, or dv du. Now, one way that you can kind of visually see that you're going to end up with a dx dy thing, doesn't work like this, but you can kind of see these derivatives with respect to u and v, you can kind of think about them, doesn't really happen. Cancel and we get what? Derivatives with respect to x and y, and that's what we started with. So we end up with this conversion factor. Now let's take a look at something we've already had before. Let's take a look at polar. In polar, we know that dx dy or dy dx translates to r dr d theta. So it just didn't go from the old variables, x's and y's, to the new variables, r's and thetas. We had this extra r pop out. Well, let's see if the Jacobian actually tells us that's what it should be. Well, we know that from polar, x is equal to r cosine theta, y is equal to r sine theta. So if we wanted to do the Jacobian here, we want to know how x's and y's turn into r's and thetas. So this will be the partial of x with respect to r, partial of x with respect to theta, partial of y with respect to r, partial of y with respect to theta. All right, let's see what we end up with. The partial of x with respect to r is cosine theta. The partial of x with respect to theta is negative r sine theta. The partial of y with respect to r is sine theta. The partial of y with respect to theta is r cosine theta. All right, doing the determinant, you multiply down the main diagonal, you get r cosine squared theta minus, multiply down the r off diagonal, that's negative r sine squared theta. Well, both of those have an r. If you factor that out, you get cosine squared theta plus sine squared theta, or just r. So you see, the Jacobian gives us our conversion factor of going from x's and y's to r's and thetas. By the way, this will work for spherical too, except for, well, you'd have three variables. You'd have what? X, y, and z with respect to rho, theta, and phi. You do the determinant of the 3 by 3, and you'd end up with your rho squared sine phi down there at the bottom. All right, let's see if we can actually put this into a problem, see how it kind of works. Let's put some room here. I might leave that there for a second. So let's say, it just said, find the volume of the integral over some region of r, the square root of, let's do x minus y, I think it's x plus 4y dA. So we're integrating over some region r. So what, you notice that's going to give us a volume, right? Because there we got a z dx dy. So we have 3 dimensions, so that's a volume. So what is our region? Let's say the region is the that's not spelled right. Parallelogram with vertices, let's do 0, 0, 1, 1, 5, 0, and 4, negative 1. All right, so like always, it would be helpful if we just did a quick little sketch here. So, so let's see, we get 0, 0, 1, 1, 5, 0, and 4, negative 1. Okay, so there's our parallelogram looking thing. So we want to integrate across this region. Now we can do this in rectangular. It would be messy, but we definitely could do it. But notice how many different integrals we would need. Let's say that for fun, that we did dy dx. Well, in this region, what does y run from? For as we start moving this way, y runs from this line up to that line. But then it changes. Y is still from the bottom line, but then it changes to a different top line. So that's a 1, 2 integrals. And then over here, the bottom changes to this. The top one doesn't change. So that's at least 3 integrals we have to set up for this region. Maybe that there's a better way to do this. Well, the type of things that you want to look for when you're thinking about using the Jacobians is if you either have a lot of equations in the region that show up over and over and over again, or show up in the argument. So let's come up with the equations for these lines real quick, and I'm going to just shortcut this for time's sake. If you go and find the equations for all these lines, this is x minus y is equal to 0. This would be x minus y is equal to 5. Let's see, this one would be x plus 4y is equal to 5, and x plus 4y is equal to 0. Okay, so that's the equation for all four of those lines. So notice we have a lot of repeats here. Well, you'd expect that in a parallelogram because the sides are basically the same, just shifted up or down. And lucky enough for us, notice that the argument actually also has those pieces in there. Okay. So if I'm going to make this substitution, let's come up with, let's let u and v be these two things. Let's let u be equal to x minus y, and v equal to x plus 4y. All right, I guess I'm going to have to remove that. All right, so that will greatly simplify our region. So if we do that, what do these four equations become? Well, these two over here, the x minus y, become u is equal to 0, u is equal to 5. V becomes v equals 0 and v equals 5. Okay, so now if we take a look at our new region over here, it doesn't matter which axis you call u and v, it's up to you. By doing this transformation, by making this substitution, we've changed our parallelogram region into, well, a square region in this case. So as you can see, this would be much easier to integrate across than this would be. Unfortunately, you're going to see that this area and this area are not the same right now. So what is the scaling factor that goes along with it? Well, to do that, we'd have to find our Jacobian. So from a second ago, we saw that this is true. X and y with respect to u and v. It's in here. U with respect to x. Oh, upside down. X with respect to u. X with respect to v. Y with respect to u. Y with respect to v. So this says that we have to take the derivative of x with respect to u and v and y with respect to u and v. That means over here that these functions have to be x as a function of u and v and y as a function of u and v. So this means this x as some function of u and v and y as some other function of u and v. So to do this, what you have to do is take this system of equations, take these two equations, and solve that system. Solve one for x, solve one for y. The good news is you don't have to do this, and most textbooks don't show you this, but you don't have to do that. There's a way around it. Sometimes you have to do it because in this case, our arguments here were exactly what u and v ended up being. If this argument here, let me change this a little bit, just had just an x in it, well, you'd have to take this system of equations and figure out what x is in terms of u and v to plug it in there. But since this argument got replaced exactly with our substitution, you don't have to do that. Well, here's a hint. What we're looking for is this, but we have u and v in terms of x and y, so we're actually able to find, we can find this if we wanted to, but that's not what we're looking for. That's the reciprocal. The good news is this is actually equal to the reciprocal of that. So we can actually figure out what this is and just flip it over to figure out what we want. So let me give us just a little bit of room here. So what would our Jacobian for this be? Well, we can't use this one, so we really want u and v with respect to x and y. Okay, so partial of u with respect to x, partial of u with respect to y, partial of v with respect to x, partial of v with respect to y. Okay, so looking at our equations here, partial of u with respect to x would be 1. Partial of u with respect to y is -1. Partial of v with respect to x is 1. Partial of v with respect to y is 4. Doing the determinant, multiply down the main diagonal minus multiply down the other diagonal, so we get 5. However, that's not what we want to use here, because remember, this is the derivative of u and v with respect to x and y, we need the derivative of x and y with respect to u and v. So we need the partial of x and y with respect to u and v will be the reciprocal of that. Okay, so believe it or not, we can now set up everything that we need to change from this world over to this world. So I'll stick it right here in the middle. I think we got room. We're going to do the double integral. Now our region isn't R anymore. This was the region R over here. A lot of times we call this R prime. We're going to do the double integral over R prime. This is going to be the square root of uv times the absolute value of this Jacobian, x and y with respect to u and v, dA, where A is now this region. So we're going to do the double integral, square root of uv. This Jacobian was 1/5, and dA, it doesn't matter which way you do this, du, dv, dv, du. What does u run from in this region? It runs from 0 to 5, and v also runs from 0 to 5. So the idea here is, one way to think about it, by making this change of variables, by going to a new world of u's and v's compared to x's and y's, this region ended up being about 5 times as big. So to compensate, we'd have to multiply by 1/5 to even it out. So this would give us 5 times the volume if we didn't have that conversion factor in there. So changing from one world to a new world can be very, very helpful. Make sure that you can finish up that integral. It's not too hard to do from now. So going from one world to another world can be very, very helpful. Notice the integral was much, much easier to do compared to what we started with.